Alright everybody, this is a video that's going to explain the connection between what's happening here in the axon during an action potential and relate it to the graph that we see when we're describing this change in the membrane potential. Now, I'm going to assume that you are very familiar already with what happens here in the axon, so I'm not going to spend a lot of time explaining, why this happens or why that happens. And I'm really going to spend more time sort of connecting these two. So just to give you a heads up on that. So here you can see we've got our setup. There is our axon here. We've got in the middle, or inside of the axon, a large number of potassium ions. These are the yellow circles here. And on the outside, we've got a large number of sodium ions, both positive ions. But what we see here is that we've got a concentration gradient on both sodium up here and potassium down here, as well as this difference in potential. We've got a lot more positive charges outside than we do on the inside, so as a result we have this bit of a difference in this membrane potential, and we measure that using millivolts. So if we go to our graph down here, what we are seeing is this represented, I'm going to get my pen here, this represented as this line here, this minus 70. That is our resting potential. Now, because of something happening in the cell body that causes some sort of disturbance and this gradual increase in this this gradual decrease or depolarization happening just at the start of the axon, it's enough to trigger the sodium gates and causing them to open. So this green gate right there. So if we look at this on our graph, you can kind of see that this is represented by this slow sort of increase. So this is that slight depolarization that edges up towards this sort of threshold right here. This is that magic number now. Sometimes it's minus 55, minus 50, minus 45. Different sources will have different sort of values for this threshold. But once it hits that, that's going to trigger the opening of those sodium channels. And once that happens, that sodium channel will open up. And by that I mean this channel here. And when that happens, sodium ions are going to fly down their concentration gradient, or their electrochemical gradient, because not only do we have this concentration gradient, it's also very negative on the inside of this axon, relatively speaking, and they're going to come flying in like that. Now, what happens is when that happens, the inside of this axon now becomes very positive, and you can kind of see that, right? Like, look at all these sodium and potassium ions, and again, they're both positive. And on the outside, we don't see a lot of those positive ions here at all. And so as a result, we see this big spike or change in this membrane potential, again, comparing the inside of the axon to the outside of the axon. And if we were to sort of scroll back down to our graph here, we would see this as this spike that shoots up like that to about plus 40. So there it is, there, about plus 40. And that is the result of what is happening right here. All of these positive ions now inside of the axon, making it very positive on the inside compared to the outside of the axon. So now looking back at the axon, we now remember that, okay, so once these sodium ions come flying in, the sodium channel now closes and it shuts, and it won't open again until this axon is back to normal, or is back at resting. The sodium channels close, and at this point, the potassium channels open. And when that potassium channel opens, you can kind of see here all of these potassium ions inside, and the fact that you've got this very positive inside axon, inside the axon here, compared to the outside. These potassium ions are going to basically move out. Like that. There we go. And just to help sort of explain what else is happening here, every once in a while you might have an odd sodium that leaks out like that. All right, so there we go. That is now what happens when that potassium channel opens. Potassium comes flying out of that channel, going down that electrochemical gradient. So let's take a look and see how that impacts this graph down here now. We have just seen, again, like I said, the sodium channels now closing and the potassium channels now opening. And when that happens, we saw that there was all of these potassium ions leaving the axon. And if we go back here, you can see, just do a quick visual scan here. We've got a lot of positive ions now back on the outside compared to the positive ions on the inside. And that is then registered in the graph as, if I can move my picture here we go, as this drop in that membrane potential there. And you can see this sudden drop is the result of the potassium now leaving the axon, and it hyperpolarizes to about -90, like that. So we're now sort of seeing this shape that we often associate with an action potential, and we're now seeing how it connects to this axon, but we are not yet done. So we've got a problem here. This channel now will close. So the potassium channel at this point will now close once it's hyperpolarized, and it will not open again until everything is back to normal, once this is back at resting. So both now the sodium and the potassium channels are now closed. There is this issue we have where we have a lot of sodium ions now on the inside and the potassium ions on the outside. And we have to fix this, and that's where these sodium-potassium pumps come into play. And when that happens, you are going to see the sodium-potassium pumps. Again, we looked at that ratio, 3 sodiums out for every 2 potassiums in. And, oops, and I know that this is, ooh, well, that's not supposed to happen. I know that I'm not doing the right sort of, it's all kind of moving around here. Like that. All right, and I know I didn't do the right numbers, bear with me, but you get the idea. 3 sodiums out, 2 potassium in, and eventually what's going to happen is, oops, out there like that, it's going to restore that action, this potential across this membrane, so it is now back to -70. And now looking at our graph, this is shown as this slow rising again back to that -70. So from here really to here is that sodium potassium pump taking all of those potassium ions that got sort of pushed, or not pushed, but moved to the outside of the axon, pumping them back in the axon, and those sodium ions that are now inside the axon now pushing them out of the axon. And when that happens, you slowly get things restored. And when you basically get to that -70, this axon is ready again to fire. So that is how we explain how all of this works. This is basically the graph that describes what happens when this axon depolarizes, repolarizes, hyperpolarizes, and eventually gets back to that resting potential again. Now, keep in mind, the one thing I did not do is talk about, what happens to this area immediately adjacent to it. This area will undergo the exact same changes, because once this thing starts to make those sodium ions come in, it's going to trigger this channel to do the exact same thing, and all the way down the axon it goes. So you can imagine that shortly after this one depolarizes and starts its sort of sodium's going in and potassium's going out, this area will start to do the same thing, and you'll see that same type of graph taking place, except in this case it'll be mapping this area here, or just describing what's happening here at that membrane and the membrane potential. All right, I hope that helps. That's basically how this graph connects to the axon, and yeah, there it is. All right, bye.